Hi and welcome to this short clip going through a slightly applied nucleophilic addition exam question. So like I've said at the top, the question isn't actually that hard once you've realised what it is you have to do. Like many questions, that's half the challenge, isn't it? Realising what you have to do. So the mechanism itself is not difficult, it just requires a bit of recall work to get it in your head and in your long-term memory. But this particular question has a molecular structure that has several different places where A-level mechanisms that you might have learnt can be applied. So you've got to think for a second, try and decide not just where in the molecule you need to look at, but also which mechanism you need to use. Once all that's sorted out, the question will slot together for you and it'll make a lot more sense. So looking at the question, the first two parts are fairly straightforward because it's literally just simple recall. So the first one asks you to write a chemical or describe a chemical test to confirm that both cinnamaldehyde and methyl cinnamaldehyde contain an aldehyde functional group. So when we put this on a test, we found that most people understood that it was Tollens reagent, plus said that if the silver mirror forms, therefore that's a positive confirmation of an aldehyde. So the second one has 3 points you need to make. First one is to add 2,4-DNP and check for the formation of an orange precipitate. That would only happen in the presence of a true carbonyl such as an aldehyde or a ketone. And then you recrystallize your precipitate and measure the melting point, and you compare the melting point to known data. Now, the next bit is where people have struggled a bit. So it's the cinnamaldehyde is react with HCN using a mixture of H2SO4 and NaCN. It says describe the mechanism for the reaction of cinnamaldehyde with HCN and show the product formed. So let's pop a bigger picture of cinnamaldehyde up there. Okay, so we've got 3 different places where mechanisms could occur, like I suggested earlier. So all 3 highlighted parts of the molecule are places where A-level mechanisms could happen. So I think where people have struggled a bit on this question is to choose which part of the molecule the HCN is going to react with. So let's pause for a sec and just look at HCN for a minute, see what it actually is. So firstly, HCN is a weak acid that forms the Cn- ion. So the Cn ion, the cyanide ion, has a triple bond between the carbon and nitrogen. So we need to think about the dot cross diagram for it to fully understand how it's going to work here. So if we start with a dot cross diagram and with our triple bond, we can now work out how many electrons are left for the nitrogen and how many electrons are left for the carbon. So the nitrogen is in group 5, so it's got 5 electrons of its own. So the nitrogen now has 8 electrons in the outer shell. So seeing as carbon has 4 electrons of its own in its outer shell, it needs a further 2. So if we put the 4th electron that carbon has itself in as a little circle, you can see it now only has 7 electrons. So clearly what has to happen is a new electron has to be gained by the carbon. So we've now got our nucleophilic species. Why is this a nucleophile? It's because it has a lone pair of electrons on the carbon which can be donated to a dative covalent bond. So you've probably spotted that the nitrogen also has a lone pair, but this doesn't contribute to the negative charge, so this won't be what attracts to whatever this nucleophile is going to react with. So now we know it's a nucleophile, we can say that our mechanism and our reaction site are going to be the aldehyde part of that molecule. So this allows us to disregard the benzene ring and the carbon-carbon double bond elsewhere in the molecule. They won't be affected by the presence of a nucleophile. They would require an electrophile in order to react. So now we can clear the screen a bit and have a go at doing the mechanism. So the first thing to do is to draw out the structure of cinnamaldehyde in a way that allows us to actually put the mechanism in. So now we can convert everything into displayed form. We now need to put in our dipoles. So then we can insert the nucleophile, and we can show it attacking the delta positive carbon on the polar carbon double bond oxygen, which obviously causes the pi bond in the double bond between carbon and oxygen to break, so 2 electrons will move onto the oxygen atom. So what happens is your oxygen atom becomes negatively charged. It's got a lone pair of electrons now, and I've labelled in a new colour an H+ ion that would have been from the HCN originally described in the question. So being negatively charged, the oxygen atom with its lone pair is attracted to the H+, which then forms a bond, which now gives us our product of the nucleophilic addition. So your first mark comes from the correct use of the nucleophile and the curly arrow to the carbon in carbon double bond oxygen. So making a bit of space to annotate it, your second mark comes from the dipole on carbon double bond oxygen and the curly arrow onto the oxygen atom. So your third mark is the correct intermediate structure, the correct charge on the oxygen and the curly arrow to the H+. And your fourth mark is for the correct final structure of the product. Okay, so that takes us to the end of the question. Hopefully it's been a useful insight into how to cope with a question like this. As always, thanks for listening, and until next time, see you soon.